going to cover the trapezoidal rule. And all we really have to do to understand the trapezoidal rule is remember everything that we learned about LRAM, MRAM, RRAM, all of those. If you remember, when we did LRAM, we used left-hand endpoints, okay, to calculate the areas of all these individual triangles, and then we added them together, okay? That would be LRAM. And all of these widths were the same. You know, the width of this rectangle was the same as the width of this rectangle, right? And then we added all of these areas together. Okay, we added area 1 plus area 2 plus area 3 plus area 4. All right, that was what we did with LRAM, MRAM, and RRAM. Well, the trapezoidal rule works exactly the same way. Only what do you think is the difference? Sorry for that interruption. Let me start over. The trapezoidal rule is just like LRAM, where we're going to add up the areas of a bunch of rectangles, only instead of adding up the areas of rectangles, we're going to add up the areas of trapezoids. Okay? So, instead of the picture that I have up there, we're going to have trapezoids that we are adding up the areas of. All right? And so, to do that, we have to start with the area formula for a trapezoid. So, if you remember, the area of a trapezoid is the average of the bases, base 1 plus base 2 times the height. Okay? And, you know, if we think of how this would work out, okay, in terms of an actual function, and I'm going to try to keep this explanation as short as I can, but it will take me a second. You know, if I call this first, let's say this is my first endpoint right here, x sub 0, okay? And of course, then this point up here would be y sub 0. And let's say that my next division is here at x sub 1, which would make this point y sub 1. I'm only going to go a couple places here. I'm going to go 2 more. I'm going to go x sub 2, and I'm going to go x sub 3. So this would be y sub 2, and this would be y sub 3. I'm just doing some labeling now. All right? If I wanted to find the area under the curve for this little diagram using trapezoids, okay, let's say that this right here was my first trapezoid. All right? Well, it's the average of the bases. Well, what are the bases? The bases are y0 and y1. So this would be y0 plus y1 divided by 2, okay, times the height. And I'm just going to put h for now. Okay, we know that it's going to be this distance in here is going to be h. But let's just put h for now. The second trapezoid is going to be y1 plus y2 divided by 2 times h. Okay? And the third trapezoid, this one right here, would be y2 plus y3 divided by 2 times h. Now, the main reason I went through all of that is so that you can understand the trapezoidal rule formula. What I want you to notice, do you see that after I simplify this, there's going to be 2 of the middle ones. There's 2 y1s, right? And isn't there also 2 of the y2s? Right? But the ones on the end, the y0 and the y3, there's only one of those. Do you follow me? Okay. So that's why I wanted to go through this short explanation so that when we get to the actual trapezoidal rule, we understand how it works. So in other words, do you see that all of these terms also have a h and a 1/2? Right? So I can factor that out. So my final trapezoidal rule formula has an h over 2 out in front of it, okay? Because every term gets multiplied excuse me, by h and by a 1/2. So I have a y0 plus 2y1, 2 of those y sub 1s, plus 2 of those y sub 2s, plus 2 of those y sub 3s, all the way up to the last one. Remember I said the last one doesn't get doubled, so I'm just going to put plus y sub k. The last one and the first one do not get doubled. And this is the trapezoidal rule. Now, in essence, though, what is this finding? Isn't it finding an integral? It's not an exact integral, but it is a good approximation. By the way, which one do you think is more accurate, the trapezoidal rule or LRAM? The trapezoidal rule. Look, I have a lot less waste up here. Okay, the trapezoidal rule is going to be more accurate. So now, what I didn't label up here is my starting point and ending point. This would be like if I was finding the integral from a to b. Okay, so the trapezoidal rule is really just an estimate of the integral from a to b of the function. All right. Now, the other thing I didn't talk about is how would I find out h? Well, wouldn't h depend on how many intervals I had? Right? Kind of like when we did LRAM. So let's make a note that h is going to be b minus a divided by n, and of course n is the number of intervals. Okay? So that's how you find h. You take the two limits of integration, subtract them, and divide by how many intervals you have. Okay? So let's look at an example. Let's find the integral from 1 to 2 of x squared dx with n equals 4, all right, using A, trapezoidal rule, B, the exact value, and C, the TI-84 program. I don't know if you remember, we don't even need to do letter C, okay? Because letter C is just your RAM program. If you remember, when we did the RAM program, if you hit enter a second time, it gave you more information. And one of the other pieces of information it gave you was the trapezoidal rule. All right, so we don't need to do letter C. We know how to do that. Okay, you do it the same way that we did RAM. You just hit enter again. All right, so let's do part A. If I'm going to do part A, then I need to use the formula. Well, first I need to calculate h. h is going to be 2 minus 1 divided by 4. All right, you subtract the limits of integration, right? And then you divide by how many intervals we have, which was 4. So this is going to be 1/4. Okay? Now, if you remember the formula, it said h over 2. Okay? So that is the same thing as 1/4 divided by 2 over 1. Right? So if you multiply by the reciprocal, that's 1/8. And that 1/8 is the thing that goes on the outside. Okay? So now we can get to our actual formula. The 1/8 is going to be on the outside. Excuse me. But now I need all these y values. All right, and so on. Well, how many do I need? Well, we're doing x squared from 1 to 2 with 4 intervals. Okay? So the y sub 0, okay, the y sub 0 is going to come from putting 1 into the function, and my function was x squared. All right? But what is this next value? Isn't this going to be 1 1/4, which is 5/4? And this next value is going to be 3/2. And this next value is going to be 7/4. All right, and then of course we have 2 at the end. So now I'm ready to plug into my formula. I'm going to have 1/8 times, I'm just going to say f of 1. Okay, because I got to plug these values into the function to get the y values. Plus 2 times f of 5/4. Plus 2 times f of 3/2. Plus 2 times f of 7/4. Plus, the last one I don't have to multiply by 2. It's just f of 2. And that is the long form of doing the trapezoidal rule. That is what your calculator will do, but we also have to have an understanding of using the trapezoidal rule formula, as we will see on some AP exam questions. So, plugging in these values, 1/8, f of 1 is going to be 1 squared, that's 1. Plus 5/4 squared is going to be 25/16 times 2, which will make it 25/8. Plus 3/2 squared is going to be 9/4 times 2 is going to make it 9/2. Plus 7/4 squared is 49/16 times 2 will make it 49/8. Plus f of 2 squared is just 4. Okay? Now, when you do all of that, okay, and simplify it, I'm just going to save us some time, I get 2.34375. All right, that's what we get when we kind of simplify that. Now, I told you that we needed to do this with the exact value. Well, this is with the antiderivative that we just learned. Okay? The exact value would be integrating using an antiderivative in the fundamental theorem of calculus that we've just spent several days learning. Isn't this a pretty easy antiderivative? Okay, it's going to be x cubed over 3, and we're going to evaluate it from 2 to 1. Or from 1 to 2, I should have said. So that's going to be 2 cubed over 3 minus 1 cubed over 3, which is 8/3 minus 1/3, which is 7/3. Okay? So this is the same thing as 2 1/3. or 2.33 repeating. That's the exact value of that definite integral. What was our estimate? 2.34375. Pretty good estimate, isn't it? Okay, so the trapezoidal rule you're going to find out is more accurate than what LRAM is. All right, and we are going to stop there for today.